Hi everyone, I am Karan. I'm in Houston right now. And to answer the question from the last presenter, yes, we can use equation discovery for parametrization, and that's what I have done, and I'll be talking about. I work as a PhD student in Rice University with Dr. Pedram Hassanzadeh, and I have used equation discovery algorithm, uh, which was also used by Laura Zana to discover subgrid-scale parameterizations from data. In order to understand Earth's atmosphere, we want to be able to numerically simulate it so that we can predict weather and specifically extreme weather events, like the Hurricane Harvey, which happened in North America in 2017, or the winter storm, which again happened in North America, and it snowed in Houston, which it never does, and everything, all the facilities stopped, and I had to survive on Coke and McDonald's burger for 3 days. So that's not something I want to do again in future. So it would be better if we can come up with uh, better ways to predict weather or extreme weather events. So I'll give you an analogy of Earth with this image of a cat uh, trying to be pretending to be dead. So this is a high resolution image of a cat, and we can imagine this as a Earth. And this high resolution image of cat would cost us more computational power to just visualize it. It has more pixels, similar to our Earth, but we don't have enough computational power to resolve everything, all the phenomena that are happening on the Earth. So what we usually do is we coarse grain everything, we use few tricks and tools, and try to resolve our Earth uh, at manageable resolutions. But at the same time, if we are doing that, we kind of lose all small details about the small scale processes. So the small scale processes which are happening like at the level of pixels are lost when we go to a coarser resolution. So for example, we can figure out that, okay, it's still a cat which is pretending to be dead, but there's a white thing here, which may be a mouse or maybe a piece of paper. So these are the small finer details which we don't know. And we try to model these subgrid scale phenomenon or subgrid scale processes. And this is called subgrid scale modeling. And to do this, I specifically choose a case of two-dimensional turbulence. So two-dimensional turbulence is fluid flowing in a 2D plane. It has periodic boundary conditions on all the sides, and it is mimicking a few of the physics which happens at the Earth scale. And the reason we choose is that we can resolve all the small scale processes uh, with the computational power we have right now, and can study different parameterizations on it. And if those parameterizations work, we can actually implement on them Earth scale models. So if you look now, we look at the equations of the two-dimensional turbulence. Here I have the continuity and the momentum equations, and similar to this image of the cat, I'm applying these filtering operation, which is simply the spatial averaging. You can imagine as the Instagram filters we have, it's same as that. And when we apply this filtering operation, we end up with these resolved scale velocities or flow variables, and also a subgrid scale term. So for my case, that's the subgrid scale term called tau, the subgrid scale stress, is the term which is representing all these subgrid scale phenomena. And this is the subgrid scale term which I want to parameterize. So the few work have been done where these parameterizations have been done using neural networks, but these neural networks are a very black box, so we don't really know what's happening inside. So new way to discover interpretable models or interpretable parameterizations for these subscale terms. A new technique has been used, which is interpretable, has a lower cost of training, and the subscale term can be represented as a function of the resolved scale velocities or flow variables. Here I've used the equation discovery method. I'll just briefly go through the process. We take the high resolution data, And then we create a library of basis functions. So this includes all the possible combinations of variables of which our subgrid-scale term can be function of. So for example, all the resolved velocities, their partial derivatives. So for my particular work, I used uh, partial derivatives of velocity, where a and b can be velocity in x and y direction in the 2D plane. And I used up to 8th order derivative. And once we get this library of basis function where we have like about 1,000 or 2,000 or lots of terms, but like that's not interpretable. So we use the equation discovery algorithm, which introduces sparsity. And this equation discovery algorithm I use is relevance vector machine, again used by Laura and Zana in their work to discover mesoscale parametrization in 2020. And this uh, this will let us end up with very small number of terms as our parameterization. So we can eventually get our subscale term as a function of resolved flow variables with a very small number of terms. And I did this process for different Reynolds number, different forcings for the two-dimensional turbulence. And every time I ended up with the same model. So this model has been known in physics, and it's called subgrid-scale model. And this model can also be obtained by the Taylor series expansion of this subgrid-scale term. So I did equation discovery, and for all the cases, I ended up discovering this model. And this model, the gradient model, has uh, excellent offline performance, irrespective of the Reynolds number we are using. Uh, so we can see here the spectra of the subgrid-scale term. The black is the truth data, and the red one is the gradient model. And the spectra match at small and large scales very effectively. The the structure, and I tested this for different filters like a Gaussian filter, a box filter, and the structure of the model discovered for all these filters for the same. Just the coefficients was dependent on the filter. So this delta squared by 12, where delta is the filter width, would be different for different kinds of filter. I also tried for the sharp spectral filter, but equation discovery failed on it. And it also supports from the fact that sharp spectral filter doesn't have a Taylor series expansion, so it is not compact. But the problem with this model is this model fails a posteriori, and because it cannot capture the energy transfer. Although it can capture all the a priori, it performs very well in the a priori metrics, but doesn't perform well at all in a posteriori metrics. So this brings us to the fact that we cannot use equation discovery blindly, and we'll need to do a few more things when we're doing equation discovery. So we have to move from the commonly used MSE loss functions, because if we used some sort of uh, filters, it will always end up discovering the leading term of the Taylor series expansion. That is the gradient model. We'll need to include some physics, for example, energy transfer in the loss function to close the gap between the offline and online performances. And we are thinking of using a symbolic regression algorithms for that. One of them is PyASA, developed by Miles Cranmer. And these discovered closure also depend on the choice of the library. So right now we just explored the library where we used spatial derivatives, but the choice of the library can be limitless. And the next step would be to use the same equation discovery algorithm in the data wave project for the gravity wave parametrization. Our work has been recently submitted to James. You guys can check it out, and I'm open for questions if you have any.
Thank you very much.